Hi everyone, it's Liam here with a summary video of the fluid mechanics and projectile motion units in biomechanics. Now what we need to know in this unit is listed here. Now I'm going to deal in this video with the first 4 points on there, and then there'll be a supplementary video dealing with the final 2. So what we need to know in this first section is the factors that affect air resistance and drag. So air resistance and drag are terms that are kind of used interchangeably, and like what affects how much we have of those factors. We need to know factors affecting the horizontal distance travelled. So when we release an object, when we kick an object, we throw an object, we hit an object, what factors affect like how far that object travels. We then, similar to last year, we need to draw 3 body diagrams and the resolution of the forces. We did that last year with the friction, air resistance, weight, and the ground reaction force. This time we're looking at objects that are in flight, so how forces act on an object in flight, and then how those forces combine to allow what's called a parabolic and non-parabolic flight path. Now the final 2 about lift force, angle of attack, Bernoulli, spin and Magnus, is we're going to deal with that in a second video. Now in the first part of this one we're going to look at the factors affecting air resistance and drag and how you can use knowledge to affect them. What they are is air resistance and drag are forces opposing the direction of travel. So air resistance tends to be used when we're travelling through air, and drag when we're travelling through water. However, they are interchangeable. We can talk about drag in terms of like going through air as well. So it's a force that directly opposes the direction of travel. So sports where air resistance and drag are quite important is things like we've got downhill skier there, we've got swimmer there, we've got a track cyclist. Now, if you have high air resistance or drag, then that's going to limit the forward propulsion. So it's going to make it harder to move forward. So you need either more energy to move forward, or the rate of moving forward would be slower. So in all these sports, they're using technology, they're using body positions to minimise that effect. Now, what affects air resistance and drag? As I've just said, that the greater the effect of air resistance, the higher the amount of air resistance and drag we have, the slower an object of travel. Now, the first point, velocity, the faster you travel, the more air resistance or drag that you're going to generate. Now, in most of those sports we just looked at before, there's downhill skiing, you've got the cyclist, you've got the swimmer, the athlete has to deal with the fact that they are going to move fast, so they're not going to slow down in order to minimise their drag. So they're going to look at the other 3 factors. Now, front cross-sectional area is the 2-dimensional shape an object would make as it moves forward. So if you imagine you're stood in front of that cyclist or a downhill skier, the front cross-sectional area will be the outline of their body. And the larger the outline of their body, the more air resistance or drag it's caused. And conversely, the smaller the outline of their body, the less air resistance and drag. Streamlining, again, we're now moving from the front of the object to the side of the object, and we're looking at what shape is the object from front to back as air travels through it. And if we remember the cyclist will have what's called an airdrop helmet. They'll be very curved from front to back, so there's no like jagged edges. The less streamlined the body, so the more jagged edges, the more like blocks of sort of body or object that it has to pass, the more the air resistance, and conversely, again, the more streamlined the object, the less drag. And then the surface characteristics. Now, generally, smoother surfaces create less air resistance and drag. And if we procrastinate back to those images, the skier and the cyclist wear lycra. There's a lycra swimsuit, there's the kind of shiny helmet. Now, it's not glass smooth. You need very, very small raises on the surface, but generally, yeah, the smoother the surface, the less air resistance and drag is caused. Right, here we can see the crazy cyclist Peter Sagan getting in the Superman position, and we'll see how quickly he accelerates. Now, looking at the factors, clearly his velocity is high, so his air resistance is going to be high, but he's got very smooth surface on his kit and his helmet. He has got a very streamlined position, so it's quite flat from front to back, but mainly his front cross-sectional area is tiny. You can see how quickly he's accelerating past these other riders. Right, having watched that image of Peter Sagan accelerating down the hill with very little effort, what I would like to look at now is pause the video and see if you can use your knowledge of air resistance to explain why Laura Trott's position in this image allows her to minimise the air resistance. Now, when answering this question, make sure you're making reference to the velocity, make sure you reference to the front cross-sectional area, the surface characteristics of the clothing she's wearing, and also the streamlined effect that she's going through. And again, a good question would identify the factor refer to the position or how that characteristic is shown in the image, and then talk about the effect that has on air resistance and subsequent efficiency of movement. So, having looked at the effect of air resistance and drag, we're now going to look on to these terms projectile and projectile motion, and look at what factors affect projectile motion, and again looking at how performers manipulate the factors to improve their performance. So, projectile motion refers to the curved flight of a path. So whenever we throw something in the air, it would follow a curved flight. Now, there are various factors that affect the shape of that curve, and the factors that we're going to look at is the speed that we release an object. And remember, when we talk about release, it can be released from the hand, we're throwing something, we could be kicking something, we could be hitting something from a golf club. So the primary factors we're going to look at now are the speed of the release, the angle with which that release is from the floor, the height of the release, so how high we're releasing it in relation to where we're aiming to get there, and also the aerodynamic factors of the object that we're throwing. Now, with the speed of release, that kind of links in with Newton's second law of motion. So the greater the speed upon release of the object, the further the object will travel. Okay, so if we think of like shot put, discus throwers, javelin throwers, they're very, very muscular, they're very, very powerful people, and that allows them to put a lot of speed on the shot put or the disc or the javelin that they're throwing. Therefore, they give it a chance to go much further. Now, in terms of the angle of release, now it's important at this moment we're imagining we're releasing an object from the ground, and we're trying to get the object back to the ground. Now, if we release the object at 90 degrees, then that object to the ground, that object is going to go vertically upwards and it's come down, it's probably going to land on our head. Okay. If we equally release at 0 degrees, it will go along the floor. But 45 degrees, if you think of like an axis of a graph, if we go like the midpoint of that and release something at 45 degrees, that's the optimal angle, not taking into account spin or aerodynamic factors of the object. That's the optimal angle of release from the ground to get back to the ground to get the distance. Now, if we release something above 45 degrees, then the problem we have is the peak of the flight is too high and it's going to come down very, very quickly. If we throw something or release something below 45 degrees, then we're not giving it enough time in flight. So, it peaks and it will come down, and it's not giving it enough time in the air to get where it's going. Okay, in terms of the height of release, this where we can affect the angle that we throw it at. So if we're releasing the object above the landing height, so we see here, we have a shot putter. And I talked about shot putters being quite muscular. They're also quite tall. So maybe if this shot putter is, 2 meters tall, the release angle maybe like 2 meters, 15 centimeters. They're releasing the ball from maybe 2 meters 20 high, but that shot put is going to land on the ground. So it's actually higher than the ground. Now, if we have what's called a positive release height, which means we're releasing something higher than where we're going, then the optimal angle of release is less than 45 degrees. And I think a shot put around about 37 degrees is the optimal angle to release a shot put, because we're throwing it from a high point. We don't have to get the ball in the air for it to travel the distance, okay, because we're already in the air. However, if the release height is below the landing height, and here we can see a golfer in a bunker, there's a raised bunker lip in front of them, or if we think of like a basketball player or netball player throwing a set shot or a free throw, the basketball player or netball player is beneath the height, beneath the angle of where they're going to. So what we need is an angle that is greater than 45 degrees. And so a negative release height, we want a greater angle than 45 degrees to allow the object to travel up and over whatever barrier is in front of them. Right, for this little practical, I'm going to be throwing 2 objects. I'm going to throw a soft cricket ball, and I'm also going to throw a shuttlecock. What I want you to be looking at is the height of the release is going to be the same. The speed of release is going to be relatively the same. I'm going to put the same amount of effort in. What I want you to see is the flight path of each object. Okay? First one I'm going to throw is the cricket ball. The second one I'm going to throw is the shuttlecock. So what I want you to look at now is reasons why the flight path of both objects are very different. Think about the mass of the object and the air resistance, and what shape of the flight each object causes, and reasons why. Okay. Right, having seen those videos of the cricket ball and the shuttlecock, you would have noticed a very different flight. Now, what affects the flight path of the object is the dominant force, okay? So if weight is the dominant force between air resistance and weight, then in that respect, you're going to get a parabolic flight. So the cricket ball, the weight was what's known as a dominant force. Therefore, it flew in quite a nice curved shape. So the first start of the flight was the same as the second half. Whereas if air resistance is the dominant force, then the object follows what's known as a non-parabolic flight path. And as you saw, as I released that shuttlecock, it travelled up quite quickly and it reached its peak, but then it came down very, very quickly. And we can see from the image here, it had what's like an asymmetrical flight path. So that would be called non-parabolic, because a shuttlecock is very, very light. It's got lots of little holes in it, so every one of those holes creates air resistance. So air resistance very, very quickly takes over, and it slows the rate of the flight path. Therefore the weight then brings it down to the earth. So looking at air resistance and weight on the objects, we need to be able to then draw a free body diagram. And the free body diagram is going to tell us which is the dominant force, either the weight or the air resistance. And the free body diagram is very similar to last year when you've done weight, reaction force, air resistance and friction. Now what we've got to remember, friction and ground reaction force are not going to be on these diagrams because the object is in flight. So the arrows that we draw, with the weight, we go from the object's centre of mass and we draw an arrow down from the centre of mass right towards the earth. Okay, and then the size of that arrow will determine how much weight there is in the object. The air resistance, again, we go from the centre of mass and we draw the arrow back opposing the direction of travel, and again we need to infer the magnitude of that force with the size of the arrow. Now the direction of travel, it must be a dotted line, and again it goes from the centre of mass and it goes in the opposite direction of air resistance, so it has to go in the direction of travel and it must be a dotted line. What we then do is we draw what's called a parallelogram of forces, which will become clear on the next page, where we can then work out which force is dominant in weight or air resistance. Right, so here we can see the shot and the shuttlecock. So if you imagine the tennis ball or the cricket ball that I threw in the shuttlecock, it will be the same thing. We can see here the weight arrow comes down, the air resistance arrow goes back, and the direction of motion is shown that way. We can see that the weight arrow is bigger than the air resistance, okay, and that means that weight is the dominant force, resulting in the parabolic flight path. Whereas the shuttlecock, we know shuttlecocks are very, very light, and as I alluded to, the little holes in them is when you throw it, it causes a lot of air resistance. So air resistance arrow is much greater, and therefore we get that non-parabolic flight path. But you'll notice that the dotted line is the direction of motion, and it kind of extends from where the air resistance finishes. Right, something else you may have to do in the exam, and this helps you find out which force is dominant. So again, we've got our shot put here, we've got our shuttlecock, or with the cricket ball, whichever one we want to think about. Again, we've got a weight force going down, as we saw earlier, and the air resistance, and we can see that the weight arrow is longer. But if we're not sure, if it's kind of marginal, again, like the weight arrow, the shuttlecock here, and the air resistance goes back, and we can clearly see which one is bigger here. But the parallelogram of forces is what we do. We draw a line parallel, so with the air resistance, from the bottom of the weight, we draw this dotted line. It has to be a dotted line again, away, parallel, at the same length as the weight, as the air resistance, sorry. And then the weight one, we draw from the air resistance, a dotted line down to the bottom. We create this parallelogram shape here. What we then do is we draw a solid arrow from the centre of mass diagonally across the parallelogram to the other corner. Now, what we're then looking for is, when it gets there, is that arrow closer to the weight or is it closer to the air resistance? And whichever arrow it is closest to. So here we can see clearly that the resultant force is closer to the weight. That tells us that weight is the dominant force, therefore it's going to be a parabolic flight path. Whereas here we can clearly see when we've drawn the parallelogram, so we draw the two parallel lines there, from the centre of mass, we draw the arrow directly across there. Now this resultant force is closer to the air resistance, so that tells us air resistance is the dominant force, therefore it's going to be a non-parabolic flight path.